Now, let us look at how we can actually interpret this, right, how we can cast this in a proper way. Okay. So, any arbitrary interface, if I can draw the interface, there is a picture also in the book which can be seen. Okay. So, this interface, I am trying to draw an arbitrary interface which has got basically two radius of curvatures. Okay. And so, this is one radius of curvature, this guy. Okay. The other guy has got this other radius of curvature. Okay. So, this radius of curvature is r I, right. This radius of curvature is r 2. Okay. This is given by say x, this is given by your y. Okay. So, these are the two. So, that this particular 2D interface, this is an interface or 3D interface, there are two radii of curvature. Okay. This is R1 and R2, R Roman 1 and R Roman 2. Okay. Now, this if this interface is now shifted or displaced outward by a small distance, right, that means it can be compared that there is a liquid vapor interface, I am trying to change the interface. Thus, the interface is deformed. Okay. Deformed means it is being displaced in some way. Okay. So, let us look at that, and it is by a small amount. So, all these things we are talking about are minuscule quantities. Okay. So, it is displaced by this, okay, and this is how it is, the interface looks like. Forgive the drawing. Okay. So, this now becomes x plus dx and this becomes y plus dy because of this small displacement. This is displaced by dz, right. Okay. So, that interface is changed. Okay. So, this interface is displaced outward by a small distance. Okay. So, that also leads to a change in area, right. You can imagine this to be like a membrane, like a balloon, right, and this balloon is actually expanded a little bit. So, naturally there is a stretching, right, of the balloon. Okay. So, this leads to a change in area. So, that change in area is given by x plus dx into y plus dy, correct. That is the change minus the xy. Okay. Here we have assumed of course x and y are sufficiently small, these are elemental kind of it is not a either this entire interface has got one radius, this is radius of curvatures at each point. So, actually the thing can be very complicated shape, right, at each point, okay, or at each interfacial, I mean at each delta A or elemental pieces, okay, we can define this two radius of curvatures. Okay. But that can also vary spatially, okay, but we are not taking that into consideration. So, if you subtract one for the other and if you recognize that quantities like this are basically 0, that is because it is a product of two very small quantities. Okay. So, that can be construed as 0. So, delta A is given by y dx plus x dy. Okay. This is what you will get. Got it? Okay. Now, the work that is required to displace the surface. Okay. Let us look at what work is done because the surface has changed. Okay. So, the work done, work required to displace the surface is basically given by delta W, right, and what it should be, it is nothing but sigma, which is nothing but the surface tension x dy plus y dx, correct. This is the work necessarily that is done against surface tension, right. Okay. So, to displace that particular amount. Okay. Now, also you should recognize that this work is basically done by what? Done by some kind of a, sorry, it is done basically by some kind of a capillary pressure. We will define the capillary pressure shortly. Capillary pressure is nothing but delta P, which is nothing but the pressure difference across the interface. Difference in pressure across the interface. Got it? Clear? So, the work that is done by this is basically given by the surface tension multiplied by the change in area. Okay. Similarly, the same thing we can also say that this is the work that is done by the capillary pressure, right. Capillary pressure which actually basically took this area and displaced it by dz, right, and this capillary pressure is nothing but the pressure difference across the interface, right. Okay. Now that we, so these are the two basically the expressions. Okay. Now, from similar triangles, okay, from similar triangles we can say x plus dx divided by Ri plus dz, right, must be equal to x by Ri. Got it? Okay. For infinitesimal displacements. Okay. You can look at it up from the similar triangle point of view. Okay. So, in this way you can show that dx is nothing but x dz by Ri. Similarly, you can do the same thing for R2, okay, not Ri, it is R1 and this is R2. You can show that y dz is divided by R2. Okay. You can show these two expressions. The first expression comes from this. The second expression you can write an equivalent expression for R2 as well, right, involving y. Okay. Okay. So, based on this, now we can say that sigma x dy plus y dx, right, must be equal to delta P, or basically the capillary pressure into xy into dz, right. That has to be true. Huh? So, that has to be true because the two works have to match. Okay. So, now we can substitute this x dy, these expressions. So, it can be represented by x dy z by R1 plus x y dz by R2. So, I am substituting the quantities. This is delta P x y dz, right. So, x y dz cancels from all three sides, right, all three expressions. So, you will basically get delta P is equal to sigma into 1 by R1 plus 1 by R2. Okay. So, this is, or we can write it as the capillary pressure is given by 1 by R1 plus 1 by R2, right. So, that is the expression, that is the Young-Laplace equation. Okay, we know this, and of course, in cases where there is only one single radius of curvature, basically the two radius of curvatures are the same as it happens in a sphere, for example. Okay. So, basically these two will be the same. So, you will get 2 sigma by r. Okay. So, and in some cases, like for example, in the case of a cylinder, one radius of curvature is infinity. Okay. In that case, you will get sigma by r. Okay. So, this is the expression which links the capillary pressure with sigma, right, and that is the Young-Laplace equation, which we will profusely use throughout the course of this course. Okay. Now, so once that now that we have done that, okay, let us look that what are the interface shapes at equilibrium, right. Okay. So, this is what we have said, that there is an interface and we can cast that how that what will be the pressure difference and sigma, and we also know that why the interface should have the minimum area. We also have a point of view from the intermolecular forces perspective, that how the liquid vapor interaction actually works, right. Now, let us look at the interface shapes. That is important. Okay. So, the interface shapes. Okay. And well, we can demonstrate it in multiple ways, but the interface shapes needs to take into account basically the surface tension effect, like what surface tension does to the interface shape. Okay. So, surface tension affects or effects, okay, on the liquid vapor. We will choose liquid vapor, that is more convenient for us. Liquid vapor interface can be demonstrated by this example. Demonstrated, okay, by considering this particular example. This is a wall, okay, and there is a liquid which basically weights the wall, right, partially weights the wall. So, this is given as z naught, this is y axis, say this is the z axis. Okay. So, there is vapor here, this is liquid here, okay, there is liquid all over, right. Okay. So, what happens is that this liquid, okay, a free liquid surface of a completely weighting liquid, okay, meets a planar vertical wall, right, and it weights a part of that wall. Okay. So, this is basically a typical example in which the interface is 2D in nature, okay, and implying that R2 is infinite. Okay. So, one part of the interface, that is one that is going inside the board, right, that radius of curvature is basically infinite. Okay. So, you can almost consider that this particular problem extends infinitely into the board. So, it is an infinite wall, it is an infinite water source, right. So, or water or whatever liquid that you can think of. So, this liquid weights partially this particular wall, it is a weighting liquid type, okay, and it shows this kind of a curvature, and it goes up the wall for about for a distance of approximately z0, and there is gravity that is acting in this downward sense. Okay. So, it is a vertical wall and the liquid is weighting the wall, and one radius of curvature is basically infinite. Got it? Okay. Now, in order to analyze this particular problem, so I think you have got a clear idea of what the problem is, right. So, we have to study what this interface actually looks like, what is the shape of this interface, right, how we can describe this interface. Understood? Okay. So, this is one of the problem. There can be many other kinds of problems that we can think of, but this particular problem shows that what the interface shape should be. Okay. And this is the interface shape at equilibrium, remember, at equilibrium. So, there can be cases, as we will see shortly, where the interface itself will be changing because of the motion. Okay. So, there can be motion of the interface, okay, because the liquid and the vapor might exhibit relative motion, but this is the interface shape at equilibrium that we are concerned with in this particular example. Okay. So, let us look at that from geometry. One by Ri, that is the radius of curvature, that the single radius of curvature, or R1, sorry, that is given by this is standard. You can actually, if you have forgotten it, please look it up. Okay. This is written in terms of the gradients, right. The zy surface is basically a zy surface, right, it is a geometric surface. Okay. So, that is the expression, that should be the expression for R, but we have to find out what these terms exactly are. What is the functional form of these terms, right. So, that is the whole purpose of doing this particular exercise. Okay. Let us move to the next one. Now, for this particular condition, whatever is the interface shape, we can apply the Young-Laplace equation. Okay, which is basically PV minus PL, because here the two phases are the liquid and the vapor, and this is given by sigma by R1, right. Okay. Now, the interesting part is as y goes to infinity, okay, as y goes to infinity, okay, and z goes to 0 and z is basically 0, okay, what we will have? You will have P v at infinity comma 0 must be equal to P L at infinity comma 0. Why is that? Just let us look at the. So, what is y equal to infinity and z equal to 0? Must be here, right, must be here. So, here what happens is that the interface is basically flat, right. Okay. So, there the two pressures of the liquid and the vapor phase must be the same, okay. There is no interfacial curvature. So, even if you apply Young-Laplace equation there, okay, the interfacial curvature is basically infinite, R1 is also infinite. So, therefore, your P capillary pressure is 0, okay. So, that implies that the pressure in the liquid phase and the vapor phase are the same, right. So, that is why we have written this, okay. So, that means liquid and vapor pressures far away from the wall are the same, right. Okay. Now, let us look at near the wall. So, that is far away from the wall. So, near the wall what happens? Near the wall means z just greater than 0, okay. Got it? Z just greater than 0, that means along the wall, okay. So, you are z is the upward axis, right, okay. So, in this particular case P v z must be equal to P v infinity comma 0 minus rho v into the hydrostatic head, got it, okay. Similarly, P L at any z should be equal to P L infinity comma 0 minus rho L into G z, right, because this is just we are adding whatever is the height of the liquid and the vapor column, right, over here. Now, in this particular, therefore, your P v minus P L, which is basically nothing but the pressure difference across the interface, right, that should be equal to G rho L minus rho V into Z, okay. Okay. So, this is nothing but your sigma by R I, right, or in other words now G rho L minus rho V into Z minus should be equal to sigma divided by 1 by R I, and 1 by R I we have already wrote the expression what is going to be your 1 by R I. So, therefore, or G rho L minus rho V to Z divided by sigma minus 1 plus dz by dy square minus 3 by 2 d square z by dy square must be equal to 0. Got it? If you do not understand, just look at it. So, what we have done is that we have taken this expression, right, this is already there, okay, and we have applied it here, right. This is a straightforward application of the same, right, and we have brought things to the same side, okay. So, this is the expression that we get by considering close to the wall. Away from the wall we are not bothered, the pressures are the same, right, the curvature is non-existent, right. So, close to the wall is what we are really interested in, because there it shows that curvature, right, close to the wall is where it shows that curvature, correct. So, this is close to wall, not far away from the wall, okay. And this happens, for example, if you put a liquid in a capillary tube or through, if it tries to rise through a narrow channel, right, or a, so that is the kind of curvature that you would expect the liquid to show, right. Okay. Up to this part it should be clear. Now, we take this expression and try to see how we can get a more simpler form. So, we multiply by dz by dy, this expression, and integrate the same, what we get is G rho L minus rho V Z square. You can work out the math individually. So, I would just show the expressions. Right. Okay. So, this comes with the boundary conditions are at y goes to infinity, okay, once again away, far away, and z going to 0, okay, dz by dy should also go to 0, correct, because the curvature becomes non-existent. There is no relative slope between z and y, okay, that interface anymore. So, this should lead to C1 going to 1. Okay. So, in other words, so that is one boundary condition at y equal to 0, okay, that means absolutely at the wall, right, at the wall y is equal to 0, dz by dy at y equal to 0 approaches infinity, right, okay, because it meets how it meets the surface, okay, at it approaches actually infinity. So, therefore, using these two boundary conditions and this expression, okay, we solve for z, right, at y equal to 0. That means, what is the rise or basically z naught, okay. So, z naught is basically therefore given by 2 sigma by rho L minus rho V into G raised to the power of half, okay, it is raised to the power of half. That is z naught, that is the height through which the liquid actually moves, okay. We can also show that y by LC, we will define LC shortly, do not worry. So, this is if you solve for the whole thing, it is more complicated. Okay. This particular expression basically shows the shape of the interface. We will see that what LC is, do not worry. So, LC is basically given by, it is just an expression and okay, got it. Okay. This has also got a formal name, it is called the capillary length, it is a characteristic capillary length basically. Okay. So, if you look at this expression, what does this expression actually give you? This expression actually tells you how y is varying, right, y at the interface is varying, okay, as a function of z, right, at different z's. What is the value of y, right. So, that is how, that is a functional form, right, and it is, we have cast it, we have normalized it in terms of the capillary length, got it. Okay. So, this is the intercept that it makes with the wall, okay, and this is the dynamic shape of the interface, okay, under steady state conditions obviously, okay. So, there is no interfacial movements as such, okay. So, what we have done, we have just used geometry, we have used the definition, the Young-Laplace equation, and we have been able, and we have integrated the same and we have shown that this is the total expression, that of course you need to work out the math, that how did you get from here to here. Okay, so that is a lot of algebraic steps. Okay, you can show that this is the expression that you get using these boundary conditions. These boundary conditions are pretty simple. Away from the wall there is no pressure, the interface is flat basically. Okay, and at y equal to 0, that means at the wall, right, at the wall, okay, you have your gradient of dy dz by dy, because it is a completely wetting liquid, that is what we told. Okay, that should actually go to infinity. Completely wetting means the contact angle becomes actually infinite, right. I mean the contact angle becomes actually 0. Okay, so here you can see the mating is like this. So the mating was something like that, right. Okay, so here we are talking about that. Okay, so naturally that curvature we have taken into consideration, right. Okay, so so this shows that this is the total expression. Now we can do some simplifications, say for example for small tubes. Here we have solved it without mentioning what is the physical scale of the problem, right. For small tubes what happens, the radius of the small tubes is much less than LC. LC is basically the capillary length, right. Okay, and Ri is basically constant. Got it. Okay. So constant Ri is constant along the interface, and you know its value is basically given as r cos theta. Okay, where cos theta is basically whatever is the contact angle. Okay, that it makes. So for small tubes we can write a slightly simplified version. There can be other things also, say for example your sigma can be a function of temperature, it can be a function of different molecular species, okay, where x is basically the mole fraction of ith component, you know the standard, and T is basically the temperature. So because surface tension can vary with temperature, right. So even if you have this particular problem, the same problem that we took, okay, right, of course this flattens out. So here for example there is a temperature gradient, say for example. So here the temperature near the interface may be high, here it may be low. Okay, so if I plot the temperature on the other axis of the interface, let's say this is a hypothetical wholly, that this is the z axis, this is the temperature axis, right. So you are plotting it across the interface, this is still y, okay, for you. So across the interface, say the temperature, let us assume there is some initial value, so you can get the temperature going like this, say for example. It can be a linear temperature like that, right. So there is a temperature differential of delta T that is created along the interface, right. We are not concerned about the depth at this particular point, it is along the interface there is a temperature gradient that is created. Okay. Because of this temperature gradient, what will happen is that if you plot the corresponding surface tension now, that surface tension will also show a gradient, is not that so? So surface tension here will not be the same as surface tension here, right, and surface tension here will be different from that, correct. So there is a variation in the surface tension, because surface tension is a function of temperature, like all properties it is a function of the temperature also, right. There can be also one other thing, we have assumed that this liquid is of pure liquid, right. Okay. It can be a mixture. Okay. So for example we can take a ready example, say for example you take a pipe and you just pour some diesel into it. Diesel is inherently multi-component in nature, it has got multiple components, right. So this liquid can have x1, x2, lot of components, right, and these components need not be the same across the interface, right. There can be more component, there can be more for example x1 in this region compared to this region, right, close to the interface, right. So that leads to what? That also leads to a change in the surface tension. Surface tension of each liquid is different. So when you determine surface tension of a mixture, that will be also different because it is a mixture of different species, right. So moment you actually have this kind of a multi-component system. Along the interface there will be a lot of variation in surface tension as well, right. So, there is a variation, there can be a variation in temperature, there can be a variation in species concentration. All these will lead to, there is a surface tension gradient basically. So, there is what we call a d sigma by dt or a d sigma by dx, dy, whatever you call it, okay. There are terms like this. Now, in this previous analysis, what did we assume? We assumed that the surface tension was basically constant, right. Is not that what we did? We assumed that the surface tension was basically constant everywhere, right. When the surface tension is not constant everywhere, like for example, in this particular case that we mentioned, right, okay, there can be actually flows or velocities that can be introduced within the liquid, okay. From high surface tension and low surface tension, you have a difference in surface tension. So, basically you have a difference in pull, right. So, this can actually drive a liquid flow, okay. There is a formal name and we will come to it a little later when we do the sessile droplet. This is called Marangoni flow or Marangoni convection. It can happen due to concentration gradient, which is basically the species gradient, or it can happen due to temperature gradient. I mean temperature gradient of surface tension's dependence on temperature and surface tension's dependence on the component, okay. So, what we have done? We have determined the shape of the interface, we have understood what the interface should look like, right. We have established the Young-Laplace equation and we know that how the molecules actually behave inside the liquid and close to the interface, right. Now, we will start with, we will introduce the problem here and complete it in the next lecture, that weighting and contact angle. This is a problem, this goes into a very standardized problem that we need to understand, and we will do Marangoni and all these other flows in here. That for example, this is a very common phenomena that you have seen, right. You spill coffee, you spill a lot of water on the surface, sometimes you see that this forms this nice spherical cap type of a droplet, correct. Does it not form? It forms that spherical cap kind of, this is a substrate, right, okay, and this is the liquid and this is the vapor, right, okay. Now, this is a very typical scenario. Now, you have all the three phases now existing at this point, basically across the circumference, all right. Okay. How to analyze problems like this, okay, because this is a very common problem. This happens not only every application will have this sessile droplet. This is called sessile droplet. So, this has got applications from pharmaceutics, right, pharmaceutics to surface patterning to coating, right, got it, okay, sensor development. You name any application, it will have sessile droplet, okay, one way or the other. So, it is important to know how we can analyze this sessile droplet, what are the flows that are introduced within this sessile droplet and how we can actually state. So, while we actually do this, we actually will look into the effect of surface tension and other things on the sessile droplet evaporation phenomena, evaporation and the dynamics of the sessile droplet, okay. So, this is one of the first specialized topics that we are going to enter immediately. So, I think you understood what we did in this particular hour. So, we covered all this interfacial physics as much as we could, okay, and now we are going to analyze this particular problem, the weighting problem, and how you determine the contact angle, okay. So, we will see you next class.